thank you. Thanks for the invitation, and I'm very glad to be here. Even though I don't see many faces, it's great to talk about some of what I've been doing in strong field light matter interaction. I'm a theoretician, so I don't do any experiments in the matters. That's why they're theoretical written in the title. So it's mainly about models, theoretical models, either analytic or numeric, that I use to either interpret or analyze or understand experiments done using light and matter. So first, maybe I'll try to explain a little bit the context, why I do that, what do I want to study, what do I want to understand, and I'm not entirely sure what is the public here, so it's maybe a bit broad. I hope it's not too broad for you, but we'll see as it goes on. So here are a few acknowledgements before I start, because I'm not entirely sure to where I'll go in my talk. So these are people with which I've been working on these topics. And so let's dig in. What do I want to study? I hope you see the titles of the slides. Well, I want to study light and matter interaction. So obviously, that's what you see when you send light on matter.
Marie, I think you can hide these panels. I think.
Okay, more.
Hide video panel or something like that.
Hide name, hide video. Is that it?
You can hide everything, I think, or you can.
Names, no. Hide disable annotation. Optimize for video clip. I don't know. Show. I don't see anything else that I can hide. Maybe if it's below here, it won't hurt too much.
Now it's not very sharp anymore. I don't know what happened.
Then maybe that's the
last thing you did was.
No, the last thing I did optimized for video.
Yeah, this better. I think you can leave it like this. I mean, the panel below. I don't know. Okay.
Sorry. Okay, then. So I study light interaction of light with matter. So today I will read, and I concentrate not only today, but usually I concentrate on the gas phase. There is a lot of interesting strong field processes happening in the common phase, and in particular in the solid phase, and it's a very active field of research too. But I mainly concentrate on the gas phase, so that's what I'll talk about today, and also mostly on non-relativistic interactions. So basically, the equation that I want to solve to understand what's going on is the time-dependent Schrödinger equation. However, of course, this can be arbitrarily hard to solve it in general, so it really depends on the system we're looking at. And so the usual methods that people use to understand what's going on when you have interaction between light and matter is, of course, time-dependent perturbation theory. As long as the field is classical, which is also what I've been using today, the Hamiltonian can be decomposed into two terms, and if the field is weak enough, then it can be seen as a perturbation, and in that case, time-dependent perturbation theory allows to compute probability of transition between states that can be understood by a picture of absorption or emission of one or several photons, depending on what order of time-dependent perturbation theory you go to. So this is really great to understand many processes happening in light matter interaction, but in some cases it's not enough. Basically, if the field is too strong, in that case, it cannot really be considered a perturbation anymore, and we kind of stuck with the time-dependent perturbation theory. But we still can say some things, and to be able to say things and solve things, we need either to do approximations. One of the most popular, and the one that I also use a lot today, is the single active electron approximation. It's not mandatory, we can go beyond, but it's often used. So basically, it's one electron living in some kind of pseudo potential that represents the remaining of the atom or the molecule, so both the nuclei and the remaining electrons. Or another way of understanding what's happening is to use model systems for which everything can be computed. And of course, we won't have in that case a quantitative description of an experiment, but rather an intuitive picture that can help to understand the physics that is behind all the processes we see. So I'll try to maybe illustrate a little bit more what I mean between the difference between time-dependent perturbation theory and strong field. Why do I need really the time-dependent Schrödinger equation, and why can't I just rely on perturbation theory? Through an example of ionization. So, because in that case, we have two different behaviors. So this would be, this would represent an atom. It's a 1D model system with a potential, a Coulombic potential, and a ground state. So if I send light on this ground state, if the photon energy is high enough, I can ionize this atom and create an ionized electron. This is one photon absorption, and it's really the photoelectric effect. So it's very well known. And we can detect the electron that is ionized, measure its kinetic energy to get a photoelectron spectrum. And on the average kinetic energy that we will measure can be deduced simply from energy conservation relations. That's really all that we can get from time-dependent perturbation theory. However, what I'm more interested in is the dynamics. So this is where I will try to show you videos of what can happen in the time domain. Do you see? Still see well, so basically I'm looking at tiny probabilities because it's a perturbation. So I will zoom a little bit on the low part of the y-axis, and I will also unzoom on the x-axis to see the electron that leaves. And then I will send a pulse with a low enough intensity so that it remains a perturbation, and a high enough frequency so that I can ionize. And as the time goes by, two electronic wave packets are created on both parts of the wave function and leaves symmetrically. So in 1D is just symmetrically x and y. Of course, in 3D you would have a wave that can be either S, P, D, depending on the ground state that you start from. So this is really well understood with one photon absorption and perturbation theory. Now, if I increase the intensity of the light and if I reduce the frequency so that now the photon energy is not high enough to ionize through one photon absorption, the behavior is very different. And here the photon frequency is so small that actually the time scale of the field oscillating is very long, very large compared to the time scale of the electron dynamics. So it makes sense to look at the instantaneous potential that the electron feels. Here it's represented in gray. To understand a bit what the electron feels, because it moves very fast compared to this dynamics. And if I stop here at the maximum of the field, here to the field is very strong, there is a potential energy barrier here that appears. And in quantum mechanics, electrons, they can cross potential energy barriers through tunnel effect. For this to be able to happen, the barrier has to be thin enough, not too large, and also the field has to oscillate slowly enough so that the electron has time to cross before the field changes sign. And that's what happens here. So a packet of electron is ionized through what is called tunnel ionization, but then the field changes sign. And so this ionized electron is actually brought back towards the nucleus, while another one leaves on the left, and you have a few interference between the two in the middle. And then this process repeats itself on the left and the right, until at the end you have this kind of, messy wave function with lots of oscillation that are actually kind of not always very easy to interpret. So I hope I illustrated that it's very different from photoionization, but now can we make sense of what I just presented, and how do we actually make sense? So the 3 steps are more detailed here, that I more detailed here in the video, are actually the 3 steps of the 3-step model that is used to understand the process called high-order harmonic generation. It's one of the very famous strong field processes that are studied nowadays. It's a very active field of research, and I'll detail more this process today. The first step is the tunnel ionization that I showed, so the electron leaves through the potential energy barrier by tunnel effect. Then also that was seen in the video, the ionized electron oscillates in the oscillating field, it propagates the continuum, and since it's brought back close to the nucleus, it can recombine to the ground state, and this recombination step loses some energy that can be emitted under the form of a photon. And it's really in a sense, opposite or conjugate of the process of photoionization that I showed just. And now this light that is emitted is called high order harmonic generation, because if we look at the typical spectrum that the electrons will emit, it looks like this. So it's composed of harmonics of the incident light. So in the experiments, it's often an IR light, so like 800 nanometer or a bit more, and up to the, I don't know, 10th harmonics or 50th or here 60. So it's very nonlinear. The intensity of the very high harmonics are almost constant up to a point where it strongly decreases. That is called the cutoff. I won't enter into the detail of how we predict the position of the cutoff, but I can if that's of interest to you. And the fact that it's only harmonics that we see, it's really a Fourier transform property of the fact that the process repeats itself every half cycle of the IR incoming laser. With an opposite sign each half cycle, and so in that case, with symmetry relation, it's only odd harmonics. It's maybe a bit technical, but I can discuss more if you want. So this process is very interesting because it has two sides of it. It's on the one side, it's a process that gives already information on the system that emits light, both structural and dynamical, and many people have used it to recover information from the emitting system, both in the gas phase and in the condense phase. But it's also used as a light source because you get a pulse in the XUV that can be very short in time. And actually the way we've generated the shortest light pulse ever produced, I think the record is around a few tens of attosecond, maybe 40 attosecond. And that's how we measure the fastest dynamics that we can measure up to now. So I'll try to illustrate a little bit both these aspects of HHG today. And I start with HHG as a probe. So it's called high order harmonic spectroscopy. It's a spectroscopy that uses the light of harmonic generation to get information of the system. I'm sorry. So I'll try to illustrate this with a specific example. It's a very broad field, of course, high order harmonic spectroscopy, but I'll illustrate this with what is called two-center interferences in HHG. That is an interference that we can see either in diatomic molecules or in molecules, actually CO2, even though it's not a diatomic molecules, but the two oxygen acts a little bit like the two atoms of a diatomic, because the highest occupied molecular orbital has two lobes that are kind of centered around the two oxygens. So what's very impressive with in the experiment is that they can, with a laser, actually align all the CO2 molecules. And in that case, if they do that, they see interesting features in the HHG spectrum. So here it's an experimental spectrum that I took from this article of 2005. And the dashed line is just the HHG spectrum of the unaligned CO2 molecule, and the solid line is the one when they have aligned the CO2 molecule before generating harmonics in the medium. And there is a strong decrease of the signal here at a specific harmonic order that depend on the orientation of the molecule with respect to the polarization of the field. And so to better see this minimum, they actually here plot the ratio of the harmonic signal here of the solid line divided by the dashed line, basically for different orientations. And so the question would be, can we link this destructive interference properties that we see here to structural interference of the emitting molecule? And how and like what model can we use? And basically, it's the minimum position and the interference contrast. Can they be related to something that's happening in the molecule? So for this, we need to use a model to link experiments and theory. The one that is the most often used to describe harmonic generation is called the Levenstein model. It was originally published in this paper in 1994, and I won't detail the entire calculation because it would be a bit long, but basically it relies on some hypotheses that are actually quite strong. First, the single active electron that I already mentioned, it's probably the less harmful, I would say. Then the bound state contributions are neglected, so basically the ansatz for the wave function only contains in the basis the ground state and the continuum state. Basically, the problem with this approximation is that it neglects the dressing of the ground state because of the field, or it does not take it into account perfectly, actually. And then the ground state depletion is neglected, so that's also not so harmful. And lastly, probably the strongest one is that plane wave approximation is used for the continuum states. And with all these approximations, you can get an expression for the signal, the harmonic signal at a given frequency omega, as a factored expression. If you want later on, I can maybe detail a little bit more, but what interests me more here is the recombination dipole that appears in the middle, so the orange one here. It's really a dipole matrix element. It's really the conjugate of the dipole matrix element you would have from photoionization. You have a continuum state, a dipole, and the ground state. And with here, the continuum state that is taken is really the wave that has the right energy to conserve energy. So it has an energy difference between this continuum state and the ground state perfectly equal to the energy of the emitted photon omega that enters here. So the claim was that since in this model the HIG signal is proportional to this recombination dipole, then the minimum should come from minimum mostly of this quantity here. And that's what I tested with the 1D models. So here, this is the HIG signal here as a function of harmonic frequency. Here it's the signal, and here it's the phase, because actually the minimum is associated with a pi phase, a pi jump phase of the phase. And as a function, and with different value of the internuclear distance r. So the color here gives the value of the size of the molecule. Here it's not CO2, it's really a model system, so it doesn't really have a name. It's close to H2 in a sense, but just because it has the same ionization potential. And what we see is indeed that there is a minimum that depends on the internuclear distance r, so a structural property. And the position of this minimum here, I can like put it here in black on the curve. So here it's the harmonic for which I have a minimum as a function of r. And in green, this is the position of the minimum of this quantity here that I just mentioned before. And actually, it's not just a minimum, it's a zero. It's an actual zero of this property that I can compute numerically.
So just
I think the questions are at the end. Well, but I can take question. Well, okay.
Was it a question though, or it was?
Okay.
I don't think there was a question.
Okay, so the zero of this quantity here I computed in green. And so that's why also we have a phase jump, because if we have a zero, really switch the phase by pi, it's if we plot it in the complex plane. And the problem is usually people, what they use to predict the position of this minimum is this scaling law that is very simple. So it's a scaling law that you obtain when you use both the approximation that I mentioned before, which is the plane wave approximation for the continuum states, and an approximation from the ground state that is to say that the ground state would be the sum of two atomic orbitals, each positioned on one of the nucleus. And in that case, you just get a cosine. It's really like a two-slit Young's interference. And so if you make this approximation, you get the yellow curve here that is indeed not too bad compared to the green one. But what we saw in this study is that if you only make one approximation and not two, if you only make the plane wave approximation, you get the pink curve here, which is very bad. And if you only make the atomic orbital approximation, you get the blue curve here, that is also very bad. So there are indeed error compensation in the fact that this scaling law that works so well. So that was one first point that we saw in this study. And that's only about the position minimum. Something that is very clear here is that the interference contrast is also very dependent on the internuclear distance, and that kind of explain why sometimes in the experiment they see a minimum, sometimes they don't see a minimum, and that was at some point very discussed in the literature. Maybe I won't go into all the technical details. I can answer questions at the end, of course. But to better understand why some has more contrast than other, we plot here not only the spectrum, but the time-dependent spectrum, a time-frequency analysis of the signal. So here it's the harmonic order in the y-axis, and in x is the time at which each of the frequencies are emitted for the internuclear position distance that had the highest contrast. So here it's this curve here in yellow. It was 1.57 atomic units, if I remember correctly. And there is indeed a hole here in the spectrum. So I can explain if you, it's a bit technical, but I can really explain all the things that we see here if you want at the end. But the important part is that this frequency is emitted at a time where the electric field is almost zero. And that's what controls indeed the contrast of the interference. And that was something that had many discussion in the literature also. Why is that so? Some people argued that it was because the field, instantaneous field, dresses the ground state and so messes up a little bit this recombination dipole. And we also showed that it's not the only explanation, indeed, and that the Levenstein model relies on some sort of classical trajectories to compute the HHG signal. And for a molecule, there is not only one atomic trajectory of an electron that leaves somewhere and comes back at the nucleus, but it can leave from one nucleus and come back to the other. And if we take that into account in the Levenstein model, the dipole cannot be factorized anymore as it was before, and that also can explain the contrast. So it's to really go further into the detail, I will need a lot more equations. So I have more equations if you're really interested. But I thought I wanted to keep time to talk a little bit about the other side of HHGs, which is HHG used as a light source. Because this is also a very broad field that is very active in research. At some point, HHG were the only way to have sub-femtosecond pulses. Now XFEL can, in a sense, also make sub-femtosecond pulses, but they are quite different. So HHG is really quite a unique light source. Here in this example, I will not use it too much as a coherent light source, more than as a very broad, since it's very short in time, it's very broad in frequency. And in that case, interesting features can be observed. And so in opto-optical modulation, which is a spectroscopy that was developed in Lund University, we use both an ultra-short, XUV pulse and an IR pulse. And why is that? It's because if I just send an XUV pulse on an atom, suppose it's mostly resonant with the transition. So here, for example, the 1s to 2p transition in helium, then the atom will absorb the light, of course. But if the pulse is much shorter than the lifetime of the excited state, then after the pulse is over, the dipole will continue to ring, which is just free induction decay, right? It has an exponentially decaying tail. And if I look at the Fourier transform of this tail, it's a Lorentzian profile or like any kind of absorption. And the phase of this tail is opposite compared to the incoming phase of the light, because it's absorption, it's like emission, but with a pi phase. And now what we can play with an IR delayed is that if I send not too strong, but strong enough IR so that it shifts a little bit the levels here through AC star shift, it will change a little bit the phase of this tail. And so now it won't have a pi phase with respect to the incoming light. And if we look at this in the frequency domain, the spectrum, we get this famous Fano profile that are asymmetric, and the shape is actually controlled by all the IR parameters, so the intensity and the pulse duration, the delay with the XUV. And it's also very state specific because the AC star shift is state specific. So the shifts of this little level here will depend on which transition I look at. So that was already known a while ago, but the optical modulation, it uses this principle at the single atom level to see something macroscopically. So at the macroscopic level, the idea is to translate the intensity dependence of this phase into a redirection, macroscopic redirection of the HUV emission. So why and how does it work? It's because in the beam, I have a macroscopic gas. All the different atoms here, they will see a different IR intensity. And therefore, the phase of the states, the AC star shift, will be different depending on where they sit in the gas. Therefore, the phase that will get accumulated, the phase of the FED, the free induction decay tail, will be different depending on where they are, meaning that the wavefront will be changed. And if the wavefront is changed, the emission direction is changed. And so there is a tilt of the emission that is controlled both by the AC star shift and by the shape of the IR profile. And that's what they see in the experiment. So that was done in the team of Johan Moritzen in Lund University for different transition in helium. So the 1s to 2p or 3p, 4p, etc. With an XUV and then a delayed IR. They see that the light is indeed redirected off axis. And the main difference that we wanted to understand here was that the NP states, they are all directed in one direction, up, while the 2p behaves very differently. Some light is sent up and the other is sent down. But since all of them see the same IR beam profile, it must be because they have different AC star shift. And that's something that we explained in the article. And so we concentrated a little bit on the 2p because it's the most peculiar. And to better understand why it goes both up and down, they changed the intensity of the IR that they sent. So it was not directly the intensity. It was actually they put an iris on the path of the beam that they sent. And as a function of iris opening, you see that if there is no IR, there is no redirection of the beam. And then first you have some light that goes a little bit down. And then if you continue to increase the intensity, some light also goes up. And this is something that could be reproduced with the simulation that I made with, here I needed to solve both the time-dependent Schrödinger equation, but also the Maxwell wave equation, of course, to get the propagation of the light correctly. And so why is that the 2p and the NP state behave so differently? And why do we claim in this article that this experiment could actually be a measure, or maybe not a direct measure, but indirect measure of the AC star shift? It's because if we look at the phase back to the single atom level of the different P transition as a function of IR intensity, all the P states, they all behave more or less the same way, very similar to the one of a free electron in an electric field. A free electron in an electric field, its average energy is just its kinetic energy, and it's called the ponderomotive potential. It has this expression, it's linear in intensity. And all the P state, they have very similar behavior. While the 2p state, the transition between 1s and 2p, it does behave differently at low intensity and at high intensity. At high intensity, it's similar to the other p states, but at low intensity, the phase decreases with intensity, and that's because it comes from a near-resonant one-photon coupling between the 2p and the 3s and 3d states that are nearby. So if we just make a very three-level system with the 2p, the 3s, and 3d, we can compute exactly the same phase as with the full grid TDSC of the helium atom. And in the middle, there is a medium intensity region. Yes, also the sign, of the accumulated phase depend on the detuning between the states. But this we did not measure in the experiment. And so in the medium, we have medium intensity. We have two photon Rabi oscillation between the 2p and the f states that actually control the phase, and that's why we have some smooth phase jump that actually strongly depend on which wavelengths we send. So if I send something that is resonant with the 5f, we have other Rabi oscillation that give biphase here. And so I find it beautiful because it's a real. In this case, we have linear behavior with 1 photon, nonlinear with 2 photons, and then at the end we have highly nonlinear with actually almost 3 electron behavior. That is the UP phase that we see at the end. So we kind of cross all the different intensity range that have very different meanings in this case. So I'm already at 30 minutes, so I do have to stop. I just wanted to mention other phenomenon that I'm interested in, and I would very be happy to discuss if you have ever heard about one of these or have never heard about one of these and you would like to know more. So I mentioned a little bit that we are building a theory group in the XFEL GDR. So I'm interested about XFEL spectroscopy recently and kind of linked to XFEL, but not only. I've worked on Auger decay in small molecules. I find it a very, very interesting subject too. So I'm beginning to be interested about ultra-fast nuclear dynamics in both these cases, which can be kind of counterintuitive, but nuclei can move at ultra-fast time scale, and it's very, very interesting. And also, if you have ever heard about run spaces or in physics, I would be very glad to discuss, because I started a mathematical project in the topology of run spaces, and I hope it can have implication in physics, but I would very much like to find someone who knows also about it in the physics community. So I'll stop here, and if you have any questions, I'll be glad to answer.
Thank you very much, Marie, for this nice talk. So there's time for questions. So if you have a question, please go to the reaction sections in the panel below and raise your hand. Nicolas? You have to unmute yourself. We don't hear you. Nicolas, do you have a question? You raised your hand, but we don't hear you. Let's see. We don't hear him, right? Okay.
I can't hear you neither, Nicolas.
Let's see in the chat. Okay, he can't unmute. Okay. Anyway, so maybe you can ask your question in the chat. I will transfer it to Marie. In the meantime, are there other questions? So maybe I can start. So in your simulations, you always solve the time-dependent Schrödinger equation and then apply some of these approximations that you mentioned in the beginning?
So yes, all these simulations that I showed here were using the single active electron approximation. So the first one was really 1D model system. So it was 1D model system with 1 electron. So in that case, it's really easy to solve the time-dependent Schrödinger equation. And in all of them, the nuclei were fixed. In the second part, it was a time-dependent Schrödinger equation in 3D for helium atom with 1 active electron living in some kind of pseudo-potential that depends on the L quantum number. I'm also working with Eleonora Lupi at the LCT because at some point we worked on methods to represent molecules with more electrons. Because we can see indeed electronic correlation in some cases in the HIG spectrum. It's not so easy to see that, because actually, if I go back to the little schemes that I showed at the beginning, basically the probability to ionize at the beginning, it's very depending on the width of the barrier. So only the highest occupied molecular orbital gets ionized most of the time, unless you have a very high intensity or very close occupied orbital here. But in some cases, it can matter. So Eleonora Lupi has a code that with time-dependent CI that can simulate HHG with a molecule with several electrons, and we want to combine it with my code that propagates in the macroscopic gas. That's not ready right now. I'd say that's a goal I'd like to do too. But otherwise, yeah, mostly single active electron and the time differential degree equation and Maxwell wave equation. The light needs to be propagated.
Okay, so if you have more than one electron, you use pseudo potentials.
Yeah.
Okay.
And in most cases, it's really quite fine. I mean, in particular in helium, in that case, the agreement between the experiment and the theory, I find it really not so bad for what we wanted to do, and also for high harmonic generation to simulate it, it's really not so bad. It really depends on what we are interested in, of course, but.
Okay. Yes. Thank you very much. In the meantime, Nicolas telling me that he cannot unmute because he doesn't have the right. So let's see if that's true for everybody. So Claudio, you have a question?
No, I can speak.
Okay. So
Do you hear me? Yeah.
Yeah.
Okay.
So Nicolas, I will anyway, we will treat your question in a second. Please,
general
Claudio.
Question. Do you aware if someone tried also to study high harmonic generation with the Floquet approach, where you have you solve the Schrödinger equation together with an external field in non-perturbative way, without propagating time? If there are I don't know if you know.
I've never tried myself, but I know for sure that some people try the Floquet approach. I think it was Madsen and co-work. I don't remember exactly the last article I read on, but I never tried. But yeah, what I'm not sure is that in the Floquet approach, at some point you also need to have not photons, but almost, right, because you shift your potential energy surface by integer multiples of h bar omega, right? Or
yes, I think. Oh no, I'm not an expert. It was just a curiosity. I'm not an expert.
Because basically with higher order harmonic generation, the approach that is more used to describe tonal ionization is more an adiabatic approach, because since the field oscillates very slowly, the electron kind of sees it as a constant static field, because it moves very fast compared to the electric field. So that's one approximation that people make, and it's sensitive more to the instantaneous value rather than its average over a period. So I don't know how well Floquet theory would represent that, but for the coupling between electron and nuclei, maybe it would be interesting though to model how this field interact with the surface energy potential of the different states. Maybe I think that's where I read about that, but no, I've never tried. Short answer.
Okay, thanks. So I think Nicolas is unable to unmute himself, so we can read his question, of course. So he's asking if you can tell more about what you would do for liquids, what type of theory you would plan to use for describing liquids.
Yeah, so thanks, Nicola, for the question. I would be very glad if we finally managed to meet to talk about it, because I know you've done some simulations on liquids, and I would be very interested about your input on that. My colleagues here, they are specialists of this because they use a lot the CPMD program that uses Carpine-Hello molecular dynamics on plane waves. I'm still learning the code, and I still have a difficulty to really. At the moment, I didn't try it on liquids. I only tried it on single atoms before to make sure that everything works, and especially the electric field. Because since I've always worked on the gas phase, I prefer to benchmark everything in the gas phase. But I'd be very glad to talk more with you. It's a shame that you can't talk at the moment, if you are forced to meet.
Yeah, I wrote that even Zoom knows that he's talking too much. So Okay, I guess you cannot solve the problem immediately, so that will be for another time. I was wondering about you showed. Did I understand correctly that you for your simulations? I think it was on the CO2 molecule where you were calculating this minimum.
Yeah, so it's not really a CO2, it's really a 1D model system. So it's hard to call it CO2. And I think it was more an H2. It had the same IP as H2, but even H2 is a bit over.
Yes, so what's the message here on the right-hand side, that you have a cancellation of errors between this plane wave approximation
and the linear combination of atomic orbitals? Yes, so that's interesting, because this scaling law here, this cosine, that it's used really very, very often to explain the position of the minimum. And it works not so bad, but it's very puzzling to me why it works not so bad, and especially it's a generic law. It does not depend at all on the system in that case. It's really just like,
yes, that would be the question. Why would that cancel? I mean,
yeah, and because approximation do not have much in common, right? It's in one sense, one is just shifting like the two. Well, it's something that we are very used to in chemistry, this linear combination of atomic orbital, and more often than not, people don't take it as a very harmful approximation. So I really didn't expect it to be so bad. And the plane wave, I understand why it's not so great. I mean, it does not behave well close to the nucleus. So that explains why it's really bad, because the recombination dipole really needs to represent accurately the continuum state close to the nucleus. And of course, the plane wave approximation would be very bad at that point of space. But the linear combination of atomic orbital, I don't understand why it would compensate this particular error. But again, it's a 1D model, so this error compensation I expected to also be there in 3D. Actually, I tested and we also see it in 2D. But I can't really be sure, right? This quantitative comparison are also hard somehow to extrapolate from 1D or 2D to 3D. Maybe the 3D case is actually great.
Okay, thanks. So there's another question on the chat. So Mathieu is on the train, so chat only. Says, very nice talk, thanks. Question, are the energies so high that correlations don't matter? Or is this the reason you need the time-dependent CI that you mentioned before?
It's more the intensity of the field than the energy that is high, and basically it's related to this. So to this part here, usually we leave if we ionize here through tunnel ionization, we leave the ion in a ground state. So there is really not much dynamics happening here while the electron leaves and comes back. But of course, there in a real life there is electronic correlation, but the electron is kind of far away and then comes back, and it's usually we don't see much. Well, actually, we see that single active approximation models work quite well for atoms that have a highest occupied molecular orbital, well, atomic orbital that is high. In molecules where the orbitals here can be close, it's harder to say that we only leave the electron in the ion in the ground state. And we could, in principle, also ionize from a deeper lying orbital. And in that case, if here we leave the ion in an excited state, for sure there will be electronic dynamics here and correlation happening in the ion. And this has been measured experimentally in aligned CO2 or N2 molecule, because in that case, they can use also the fact that the orbitals have different geometrical properties, and so that ionization can be enhanced in the HOMO -1, for example, using the alignment of the molecule with the field that would favor this orbital with respect to that one. And in that case, they do see electronic correlation, and that's mainly where we need TDCI to represent what's going on. but in atoms, most of the time it's so I'm not actually very familiar with ARPES because I never, because I do 1D models, so most of the time I don't have an angle. But yeah, I guess it's related, right? If you ionize an electron and you want to look at its angle resolution, you will need to know well how the plane waves are close to the nuclei, because it's the dipole matrix element between the ground state and the continuum state that is important. And photoionization is really the same as the recombination step that we have here, just time reversed in a sense, or conjugated. So if I think it's probably the same problem, yes.
Okay, thanks very much. There's a question from Dale. I hope you can
Hi,
unmute yourself. Okay, good.
Can anybody hear me?
Yes.
Great. Awesome, awesome. Yeah, nice talk, Marie. That was really, really interesting. I have one question. So, in the section on, so you have a time frequency analysis of high harmonic generation. Right. Yeah, I think it's the next. Yeah, right. So there's this feature on the on the TFA. This dot, right? So I hadn't noticed this before, and I checked in our results with we were using TD-DFT with LDA, and we have done a similar calculation treating high harmonic generation, and I had never noticed, but this feature was in our results as well, right? So I was really, really interested. Is there anywhere more I could read about this, or any literature that would cover this? Oh, sorry, I can't hear you now.
I think you're still mute.
Interference in particular, or
Basically, yeah, I had not put this down to an interference film, and I'd assumed, it could have been some artifact in the TFA or something. But yeah, is there anything in particular on in high harmonic generation, this particular feature?
It's a whole chapter in my PhD where I put lots of references. So basically, it was first theorized by Manfred Line. He was I think, in the early years 2000. And then there is quite a broad literature on that. And I think Lars Madsen also wrote several very good papers. But if you look in my PhD, you have really an entire section. I really made it's a few years ago, so you won't have the more recent article on this, but there are lots of references there, and I explain a little bit more